our session by welcoming the speaker and by announcing the title of his talk, Cross-lingual Research in Medical Text. And we were warned by Ondra that we should not be disturbed by what's going on the other part. Here. So I hope you won't be nervous to see me.
Yeah.
Well, the floor is yours.
Thank you so much for the introduction. Hello everyone. Today I will present our work in cross-lingual IR or search in the medical domain. So what is information retrieval in general? Information retrieval is the task of finding materials or information in a raw text or unstructured data, usually documents, where this information meets our need. Typically we call this task search engine. So, what is cross-lingual IR? The exponential growth of the internet last decade was also at the same time, there was also a growth in the content, and this growth was not limited to the English content, but it was multilingual growth. In 2001, there was a study showing the growth of the multilingualism of the internet. It showed that yes, English content is growing quickly by 800, but also there are other languages growing quickly as such, like German and Spanish by 1,500 and 1,800 respectively. Also, after about 10 years, Zuckerman made a study checking the content or the languages on the internet. What is the main language of the internet? Is it true that English is the language of web or not? He claimed that English is no longer the language of the web, and the reasons, he presented multiple reasons for that. For example, all the studies that try to estimate the languages on the internet relied on search engines, and search engines usually like English content because of online advertisement and other business perspective. Also, he showed that the growth of the internet users in in Asia or in the Arab world was multiplied by up to 25 times. The third factor he presented that all the methods that we used to check the multilingualism of the internet, they relied on checking the homepage of the website. And as we know, many businesses tend to present their website in English, as UFL, and also some websites he replicated the experiments and showing some websites like social media like Facebook or Twitter were identified as English website, and as we know it's not true because for example in Facebook 2 years ago they said that they have 1 billion users, so not all of these users are English fluent or English speaker. So we want to find a way to access this information, and it might be interesting information for us in languages that we don't speak. And this is the task of cross-lingual IR. Cross-lingual IR makes the content of the internet available to everyone by breaking these language barriers. Here's another stats about the content on the internet. It was taken from W3 Text, and as we see also English is still the dominant language, but there are many languages growing very quickly, and the information access of these languages is not easy as it is in English. Here's a small example about Google cross-lingual IR. So if I search on Google for deep learning in quotation, so I want to search for this particular phrase, I see that I find around 46 million pages in Google. I ran this query yesterday. And I removed some results videos just to show you the results. So this is the English, and as we can see, pretty much results. So let's look at the Czech query. I think I used the right phrase, right? So in Czech, we find only 11,000 results, which if I don't speak English, I will not have access to the almost 46 million pages. I will have access only to these results. And so this is actually monolingual IR, because I speak only Czech and I can read only Czech articles. However, if I don't speak English or Czech and I'm looking for like medical insurance here in Prague, Google doesn't present any Arabic results, right? It presents only English, and this is the cross-lingual IR of Google. This is how they do it. So they present the results in English, and then they tell me, okay, this is your option, how you want to understand the results, or you want to choose your own machine translation tool for that. However, 9 years ago, they had this option, translate foreign pages. So they know what languages or what language I speak, and they translate the languages from the pages from different languages. However, they removed this this option. I think it was deployed maybe in 2005 or something like this, and then they removed it in 2011. They said, people don't use it, and they encourage their users to use the integration in Google Chrome to translate the pages. So this is how cross-lingual IR in Google looks like. So in short, cross-lingual IR is the task when the queries and the documents are written in different languages, or let's say 2 different languages, and it's different from multilingual IR. In multilingual IR, I might write the query in one or more languages. It's like more general task than cross-lingual IR, and retrieve results from 1 or more different languages. In order to conduct cross-lingual IR, we have to map the queries and the documents into one space. More often, it's a language. Retrieved documents, as I showed, may remain in their original language, so the user has the option to translate it or maybe understand the message behind the from this second language for him. Some cross-lingual IR tracks past 20 years, actually, there aren't like they are not enough, or as we can see, like most of them stopped. For example, Czech launched cross-lingual IR tracks from 1997 to 2002. It was focusing on the news domain and the European languages. NTCIR, the same, launched CLIR tracks until 2010, and they were focusing on the scientific content rather than news domain. Later, they added a news task, but the interesting part of these campaigns were the scientific content or the academic papers from different languages. FIRE focuses on the Asian languages, not the European languages, and also news domain. CLEF, Cross-Lingual Evaluation Forum, also launched cross-lingual IR in the new news archives from 2000 to 2009, and then they stopped these tracks. However, in 2013, they started cross-lingual IR in the eHealth domain, or in the medical domain, and it's still running until today, until this year. It includes monolingual task, where the queries are in English and the documents also are in English, and subtask, the queries are provided in multiple European languages, and the document remains in English. The task focuses on the patient, or it tries to simulate the case when non-medical experts look up medical information on the internet. So it's a specific domain, medicine, and it's patient-centered when the people are not or don't have medical experience. They don't use medical terms when they search for their symptoms or medical conditions. queries and documents were provided in different languages, and this is like our first, this is the first system we present. The query is in English and the documents are in English, so I want to see ranked list of these documents in from the which are somehow relevant to the query or the information that I'm looking for. Our test collection in this research is adapted from these tracks from 2013 to 2015. We extended it, as I will show later. So the documents contain about 1 million pages. These pages are in English and crawled from medical websites. The queries are released in English in 2013 and in Czech and French, Czech, French, and German in 2014. In 2015, also the same. So our first contribution, we asked medical experts to replicate the translation process during these tracks and translate these queries to 7 European languages. So we cover Czech, French, German, Hungarian, Polish, Swedish, and Spanish. And by saying replication, the translation process, it was a bit complicated, or let's say not complicated, like systematic. So first they showed the English queries to medical experts, and they asked them to translate them to their, who are fluent in English and their own language. So they asked them to translate these queries to their language. And then after they translated these queries, we presented these queries to experts in linguistics. We asked them to see if there's some, if they suggest some measure edits, and then we showed the edits back to the medical doctors to see if we didn't lose any important information during the translation process. We also conducted assessment process where we showed medical experts our results, the query, and the retrieved documents. All were in English, so these also medical experts were fluent in English. So we asked them to check the query, to check the information need behind this query, what we are expecting from the search engine to retrieve, and we asked them if these results are relevant or not. They had 3 options: if this query is relevant, it's relevant, or it's irrelevant, or it's highly relevant. We published this test collection in ECIR, and it's available in LingDat for download. And the queries in 2013 and 2014 were created based on the discharge summaries. So when someone goes to a hospital for some treatment, when they leave the hospital, so there will be a file containing this information. What were the symptoms, and what was the treatment process, and what was their status when they left the hospital. So these discharge summaries actually contain a lot of, let's say, medical language, because it was written from medical expert. But in 2015, the process was totally different. They showed medical, let's say, images of medical symptoms to students, and they asked them, like, for example, here we have a red spot on my leg. So how do you describe these symptoms? So they wrote queries describing these symptoms as they usually do it on search engine to find what's going on, what's the medical condition I have. And these queries were again translated in all of these languages. Here you can find the difference between the queries in 2013, 14, and 15. So here we can see the language is like simple, and the terms are not really taken from the medical domain. So what we did here, we mixed all of these queries together, and we split them randomly to 100 queries for training and 66 queries for testing, because we want the system that we will design to be stable for these kinds of queries, if they contain medical terms or not, to make it more stable for these variants. So our contribution in the cross-lingual IR task can be divided into these bullets. First, we created the query translation system, or let's say baseline, and then we moved to re-ranking of these of the machine translation hypothesis of the queries. We extended the collection and we made it available online. We also present query expansion and domain translation approach and task-oriented and MT model for query translation and document translation. I will go through all of this. So let's start from query translation. In query translation, or in cross-lingual in general, we have two options. We have the document translation approach, where we translate the documents into the query language and we keep the query in the original form. And we have query translation approach. We keep the documents in their original form, but we translate the query. So the question which approach we will choose was always like the main problem in cross-lingual IR. We don't know which approach works better in which domain. So let's start from query translation. Before I go further, I will explain the evaluation of our system. How do we conduct evaluation? So our IR systems in general return a list of ranked documents, and this rank according to their relevance to the information need or the original query. And each result has a score. Usually users are interested in the top K documents. We don't go further, right? Like we check maybe first 5 pages or 10 maximum. We never click to see the next page in our search engine. We want to check these K documents if they are relevant to our information need or not. That's why we use P@10. How many relevant documents appeared in these highest 10 retrieved ones? We can use, like, there are many variants actually, like P@5. Some people say, okay, like P@10, maybe it's too much today. People don't look really at 10 documents, they look at the first 5. So they use P@10 as a metric, sorry, P@5, but P@10 actually is the most used one, and still I think more reasonable until today. How do we make this assessment information? As we said, we judge if each document if it's relevant or irrelevant according to the assessment process that we did before. So we have actually a GRIL file. File contains the query, the document, and the result if it's relevant or not relevant or highly relevant. So how do we conduct machine translation? We use already trained system. Here it was trained here in UFAL based on Moose's Statistical Machine Translation System. It was trained on a lot of parallel data from the medical domain, also monolingual data. It supports translation in 7 languages, from English to 7 languages. And it was tuned to translate short sentences or queries in the medical domain. Also, there's another version of each system that translates sentences or summaries, long sentences, which is not the case here for query translation. So we use this system to translate the query into English, and now we have the documents in English. We can index them to create an index for these documents, and we can use a scoring function where the input is the query and the documents, and the output is ranked documents according to their relevance to this query. So here are the basic or the baseline results of this experiment, and here's the English results. The English result actually is the monolingual results, where the query are in English and the documents are in English. So we consider this system as the reference system to our cross-lingual IR, and we are trying to reach this result as much as possible. We can see here that some systems like Swedish and Polish are not doing well, actually because of the machine translation systems themselves. Like the quality was not really good, and we noticed a lot of out of vocabularies in these translated queries, and we can see here how it affected the cross-lingual IR performance. Okay, so what we did now, we had a query. We used machine translation system to translate it to the target language, and we took one best list, the best translation. But what about other translations? We have other translations, and they contain, let's say, interesting terms or useful information. So we want to employ these translations and try to re-rank them according to towards better results, not towards better translation. Here we are not interested in the translation quality at the end. We are interested in the quality of the retrieval retrieval system. Firstly, what we did, for each query, we translated this query and took 15 hypotheses, the best 15 results. And each result, we run a retrieval for each result. And then we took we checked the hypothesis that gives the highest P at 10. And then we checked where this hypothesis ranks in the translation. Like, for example, the hypothesis number 1 or the best translation gives the highest P at 10. And then the hypothesis, let's say number 15, it gives the highest P at 10. So by looking at these figures, we noticed that in 50% of these queries, the best translation gives the best retrieval. So there's another 50% where the best translation is not the best for retrieval. So we are interested in these translations to use them instead of the best translation or one best list. The first approach to do, maybe we have, let's say, 5 alternative translations. Maybe you don't need to bother to re-rank them. What if we concatenate all of them and try to check the retrieval results? But unfortunately, it didn't work because in the alternative translations, we found some cases where the medical, let's say, or the diagnosis or the symptoms were totally different from the reality, like error in the translation. Then we moved to focus on the best translation itself in terms of cross-lingual IR. What we did, we designed a machine learning model which considers P at 10 as the objective function, and the results, the feature set was taken from different resources. For example, first we considered the SMT features like translation model or language model, reordering model scores for each translation. And then we added rank features. Each hypothesis has a rank, if it's the best one or not, and the location and the rank in the list, like first, second, third. We also designed features based on blind relevance feedback. So what we did here, we took the best translation, we sent it to the system, to retrieval system, and we took the highest retrieved documents. So we have now a pool from these documents, from these retrieved documents. So for each hypothesis, we count the term frequency in this pool, assuming that this pool contains relevant terms. Also, we used IDF for each term in each hypothesis from the collection, which tells us the importance of this term in the collection. We did the same with blind relevance feedback, but the source was different. So we used Wikipedia. The motivation here behind Wikipedia was that, okay, so non-medical experts wrote these queries. So basically, they described their symptoms, and they didn't write any medical terms, which can be observed in Wikipedia articles. If you go to Wikipedia, you will see the title written in like the medical disease or whatever, and in the abstract, the language is simpler. Like people write in the abstract, they write some symptoms related to the main disease. So we wanted to capture this information by sending this query to Wikipedia and take the count the term frequency in these abstracts from Wikipedia. So after we prepare the features, and now we are preparing the training data. So we get in best hypothesis for each query, and more precisely 15 best hypotheses. After we did some experiment, we found that 15 is enough. We run retrieval for each hypothesis, and we get the best P at 10. So now we have. So we know the best goal or score we can achieve from each best list, and we generate then vector of features for each list. We have 100 queries for training, 15 best list hypotheses, and we followed two approach. We tried first to design a machine learning model for each language, or machine learning model for all languages, language independent model. We excluded queries where we didn't find any hypothesis with results with the P at 10 more than 0, because like simply the documents the collection didn't include any relevant documents, or the translation was full of like OOVs or not correct at all. So we excluded this hypothesis from the training, or queries from the training. First, we tried the language-specific model. We trained this approach for each language, and we tried again independent model where we concatenated all the hypotheses from all the queries from all the languages together to create a training set. We noticed that the language-independent model was much better than the language-dependent one or language-specific one, because the data was much larger. Here we can see some analysis of our results for 3 languages. We were able to improve 9 queries in Czech, 15 queries in German, and 8 queries in French. We have some degradation in Czech, like 2, 4 in German, and 3 cases in French. And here are some results of the query. So the reference query is the English query, the original English query. And the Oracle query is the best result that we can achieve from any hypothesis. Bayes is the query that was created from the one best list. And best is the hypothesis as it was returned from our reranker. So we can see here the model tends to use longer hypothesis, longer hypothesis, because the score of some feature was higher, like IDF score or term frequency. And in some cases, we were able to even outperform the English query or the reference query, as you can see in the French query. This is COPD, or swollen lower limb. So here's the result of the reranker comparing to the query translation system or the baseline. We have significant improvement in all languages, but we are still not far, but we didn't reach the reference system yet. So to conclude this part, we observed that in 50% of the cases, SMT was unable to retrieve the best result for cross-lingual IR. The reranking model was able to re-rank this hypothesis from the SMT system and give the best hypothesis in terms of P at 10, not regular MT scores like BLO or PAIR. And the best way to do it is to concatenate the data from all languages or design language-independent feature to make use all of the data that we were able to generate. So now we move to query expansion. So what was the motive for this approach? The motive was, okay, so the problem is these users are unable to write, let's say, representative query for their information need because they don't use medical language. We tried to do reranking, and then we said, okay, maybe these terms or the hypothesis list from the SMT system simply doesn't contain all the terms that might be relevant to the original information need. So we should look at different sources. However, it doesn't mean that we, as you can see, doesn't mean that this hypothesis in some cases don't contain useful terms. We can see here that these terms, coronary, cardiac, or stroke, didn't appear in the best list. So if we add them, maybe we will get better results. Also here, another example from this query, white patchiness in mouse. So query expansion is the process when we reformulate the original query by adding one or more terms to it. These terms can be extracted from the document collection or from external resources like WordNet, Wikipedia, or PubMed articles. And here's one example from the training data. This is the one best list from the SMT system, and our query expansion model suggested to add these terms: kidney disease, function, dysfunction, failure. So we can see here some terms that are likely to be used by medical experts, like dysfunction or insufficiency. So how did we do that? First, we started from the translation process. We translated the query using SMT system and generated candidate terms from this hypothesis. But as I mentioned, these alternative translations maybe don't contain enough terms. So what do? We send this query. We indexed the articles from PubMed, around 25 million articles from PubMed. Each article contains the title and the abstract. So we indexed these articles. They are in English, and sent one best list to this index and retrieve the best 10 articles. The same in Wikipedia, but in Wikipedia we were interested only in the title, but in PubMed article we were interested in the abstract because we wanted to catch more. Usually the titles of PubMed articles are more like very academic and scientific, and they don't contain like symptoms or information might be interesting for us. So we want to score. We want to score these terms. We have now a huge pool of terms. We want to score these terms to see which term might contribute to the information need and which might not. So we present a scoring method by representing each term with a feature vector and use the regression model to select or to predict the usefulness of these terms. We describe the usefulness of this term by checking how much the performance or P@10 will increase when we add this term to the query. So for each query, we add one term and we run the query. I'm talking about the training. We add the term to the query, we run the retrieval, and we check the improvement in P@10. It might decrease, so the term is not relevant, or increase, so the term is relevant. So this is our objective function. We joined all the data from all languages. We ended up with 6.8 thousand training instances. So each instance is a term. And in the test, we extract the terms, or we generate the candidate pool from the resources I presented, and then we score each term using this model. However, we found another problem, that some queries are simply good and we don't need to expand them. So when we expanded them, we noticed that we heard the results. So we want to see also, not only because they are good queries or written in a good way, but also maybe the terms are not relevant at all. So we wanted to set a threshold for these terms. If the score of these terms is above this threshold, let's add it to the query or ignore it. And about feature set of this model, we used IDF from the collection to measure the importance of this term in the collection, and the frequency in the 20 translation alternatives, and the frequency in the retrieved documents using the base query from the collection. The same from Wikipedia articles and the abstract of PubMed, and the frequency in UMLS metathesaurus. What we also did, we added this term to the basic query, and we run retrieval to see to employ the scoring function itself, the retrieval scoring function. So when we add this query to the basic query, we will see that the retrieval status value, which was generated from our language model, the Richlet language model, changes. So we want to observe this change and how it contributes to the final retrieval score. We also added the term similarity, or the similarity between the term and the basic query from using Word2Vec by getting the candidate, the embeddings for each term, and summing up the embeddings with the vector that represents the query, which is also the sum of the query terms. And then we measure the cosine similarity between the embeddings of the term and the embeddings of the query, and add this score to the feature set. What we did also, we said, okay, so this term might be relevant to the query or not. And if it's relevant to the query, there is a high chance that this term will appear in the relevant documents. So we added also the co-occurrence frequency of each candidate term and the documents that were retrieved for that query, or the base query. Here are some examples from our system. So the source query is in the source language, Czech and French. The reference query is the English one, or the manual created one, and the Smt is the machine translated one. So by adding, what does it mean? By adding these two terms to the best list, the retrieval performance, or P@10, will increase from 60 to 70. So we were able to catch more relevant documents by improving the information need that is represented in the base query. And the interesting part that we can see here that, okay, so for this query we found only two terms, but for this query we found a lot of terms with high score above the threshold, and we added them to the basic query, which increased the results from 0 to 30% of P@10. So what we also investigated is the source of these terms, how the source of these terms might affect the performance of the query expansion algorithm. So the first source was translation alternatives, only looking at this hypothesis from the Smt system. And the second source is only Wikipedia titles. The third one is the abstracts from PubMed. So we tried different settings by merging these sources together, or using each one. So we can see that it's not like using the translation hypothesis and Wikipedia almost was the best system except Polish. And again, the reason here that was the bad quality of the SMT system in the Polish language, because it affects all the process of catching the terms from PubMed or from Wikipedia. What we did again, so we said, okay, so now we have the basic query, we have algorithm that can give us expansion terms. So what if we merge this approach with the re-ranking approach? So what we do, we take the hypothesis from the SMT system, we re-rank them. So we know now that we have better translation for the retrieval, and then we add these terms to the re-ranked hypothesis. The interesting fact that we can see in Czech, we were able to reach the reference system, or the English system, monolingual system, by using the re-ranker and the term selection method, and it actually outperformed all the other results, which was expected, because we add these terms to a better query, which was re-ranked by the machine learning model. So, to conclude this part, we presented a query expansion to algorithm to improve the information need in the queries, and it was designed for medical domain. By saying medical domain, we consider the source of the candidates, because we used PubMed. So if we can think about different source of candidate, not only PubMed, maybe different source relevant to our domain, the same algorithm can be applied. We also noticed that setting a threshold for term selection is really critical, and for that case, actually, we found that KLD, callback divergence algorithm for query expansion, failed to improve the results or the baseline system, because it always adds terms to the basic query. So here it's important to set up a threshold, or to try to come up with some idea to measure the usefulness of these queries. We don't need to expand the query with irrelevant terms, because then the information might be drifted to different topic and destroy the result. So we tried almost everything with SMT, like what we can do, re-ranking and expanding and query translation. So everyone was talking about NMT, so we decided to check what we can do with neural machine translation. So NMT has achieved, as we all know, much better results in machine translation than statistical machine system, and it's simpler to design. We don't have internal components like SMT, like language model, translation model, or other things. But we know for sure that it doesn't achieve well in low resources setting, and it's more sensitive to data than SMT. So, back translation in MT helps to in domain adaptation. It's a very used method to adapt an MT model for a specific domain, and which is ideal for our case, because it's medical domain, and we want to resolve the ambiguity of translation between the general domain and medical domain. For example, the word development. So in general, we don't know what does it mean, right? And but in medical domain, we know that development means the spread of trauma or something like that. So we want to solve this ambiguity by designing MT system that is adapted for medical domain only. So what we employed in our in MT development, we chose encoder-decoder architecture to design the an MT model, and we used iterative back translation as it was presented by Hong. So how we did it? First, we use the same data that we use in SMT training because we want to measure we want to make the comparison fair between SMT and NMT. Maybe it's not really easy to do that, but we tried our best. For example, we encoded all the data in NMT training using byte pair encoding, but we didn't do that in SMT, and we don't know if similar approach in SMT will change the results or not. Also we applied back translation in NMT. We didn't do that in SMT, but we think it's fair because in SMT we have language model, and here in back translation we have to we want to let the NMT model captures the same information or the linguistic information that we do usually using language model. So here's the architecture of our system. First, we designed two models, English to target to the 7 languages, and target to English using the same parallel data that we used in SMT, which is around 10 million sentences. Here we did something something different we didn't do in SMT, which is data cleaning. The first iterations in our development, actually we couldn't. The results were bad, simply bad. So by looking at we tried to analyze the results and what was going on. We noticed that the data contains some noise. For example, in Czech, we found around. By doing very basic check, we found around 1 million sentences in these 10 million sentences. So these 10 million sentences, actually, they were already chosen from 40 million sentences, scored by some adaptation method. We didn't do that. It was done here in UFAL. But even in these 10 million sentences, we found 1 million sentences. The Czech part was either in English or in some Greek or I don't know. So what we did here, we employed something very simple. We said, okay, so we want to see if this sentence in this part of the parallel data is Czech or not, or Swedish or whatever. What we did to achieve that, we say, okay, so if this sentence contains one or more stop word list from the Czech stop word list, then it's Czech. And immediately we noticed them collision between stop words. For example, in English, there is a stop word list word, it's to, but it's to in Czech. So we excluded this, for each pair, we excluded these stop words. And we cleaned the data by around 10%. So that was the first, after this cleaning method, that was the first time we were able to start outperforming the SMT system. So to achieve or to conduct back translation, we need monolingual data in the target side. Why in the target side? Because we want our translation to be fluent and educate as much as possible. So we chose 2 sources for the monolingual data. First, the document collection itself. We have 1 million documents in English, and the English side or the target side of the parallel corpus. So what we did, we are trying to improve both models, English to target and source to English after each iteration, or how we stop training. If 3 consequences checkpoint didn't improve the scores, blue score, we stop training, and then we change the initial model again. By using the new models, conduct back translation, and train them again. So at the end, we have 2 models, source to English and English to target. But what we also have, a lot of intermediate models at each after we finish each checkpoint or epoch. We save the checkpoint or the intermediate model. So we want to know which model to choose. What we have two options. We can either look at BLOS score, the model that gives the best BLOS score, or the best 1- pair, or the position independent error rate model. And why we are interested here in pair? Because in our retrieval setting, we don't consider the order, the word order. We consider the collection as back of words, so the order is not important here. So for queries, we chose the model that gives the best BLOS score and the best pair in the training data. And we tried to we run the retrieval. We noticed, okay, so we outperform the SMT system, but can we also improve it more? And what we tried to ensemble these two models: the model that gave the best BLOS score and the model that gave the best pair score. We assembled them together by giving them similar weight, 50 or 1 and 1. We didn't tune the model weights in this process. So that was the model that gave us the best result when we combined these two models together, and that was only for query expansion. For why we couldn't do that in document translation, because each time you need, for each intermediate model, we need to translate the entire collection, 1 million documents, which is pretty expensive. So we decided to choose the model that gives the best BLOS score, which is acceptable actually, because in documents we have long sentences. We are not translating short sentences like queries. So we said, okay, so let's choose the best BLOS score model for document translation. And here are the results. So in Czech, we significantly outperformed the reference system, not only the baseline, but also the reference system. And we can explain that because we have better quality Czech data for training than other data. And also that maybe my understanding or basic understanding of Czech helped me to check the stop word list and do more error analysis. So I think we have also a chance to improve other languages like we did in Czech. So first, we want to understand why NMT outperformed SMT, which was expected, right? So first thing, we observed a lot of OOVs in SMT, in the SMT translations. In Spanish, for example, we found 40 OOVs, or untranslated terms, in the queries, and OOVs because we do term matching in retrieval. If some terms are left untranslated, we simply cannot catch the relevant documents. So considering these OOVs in SMT and comparing them to NMT, we didn't. In NMT, basically, I couldn't observe any OOV. And the encoding process helped us to reduce the OOVs during translation or encoding. So that was everything about query translation. And as I presented at the beginning, there is another approach which translates the document into the query language. So documents, for each language, we translate all the documents in the query language, and we perform retrieval without touching the original query. Why we don't like this approach? We don't like this approach because it's really expensive. So each time we want to support a new language, we have to translate the entire collection, and we know that we always have new documents and something is happening. So when we index the data, it will increase every day. So we don't want to translate the entire collection every time we want to support a new language or translate the documents for maybe 10 of languages. However, we think that document translation is better than query translation. And why that? Because documents contain long sentences. and long sentences contain linguistic information and contextual information, which is important for SMT system or machine translation system in general. So the hypothesis in this field since almost 30 years ago, 20 years ago, was document translation is better than query translation. We know that, and but we don't want to do document translation because it's expensive. And until like 2 years ago, researchers still quoting this. Document translation is better than query translation, but we want to do query translation because it's cheaper and we can easily adapt a new language. However, the fact that machine translation improved a lot in the last 20 years or maybe last 5 years, so we decided to reinvestigate this fact. Is it really document translation? Is it really better than query translation? So first we used the SMT system for summary translation, which was also developed here in UFAL to translate the document. The system was trained on the same data that query translation MT system was trained on, but it was tuned to translate long sentences or summaries. So this system produces word form. Typically, right, for translation. So, but we are not interested in the translation quality as I stated. So what we tried to do, we limmatized all the data in the like parallel data and monolingual data, and we designed a new SMT system identical to this SMT form, but it produces lemma, not forms. And then we translated the documents using SMT form and SMT pre-lemma. Why pre-lemma? Because we also lemmatized the translated documents. So first we translated the documents into the forms from English into 7 languages. And then we created another index. We lemmatized these translated documents because we wanted to check how morphological analysis or processing affects the retrieval quality. We also created another index after stemming the translated documents. And we translated the documents using the SMT that produces only lemma. And finally, we created another index for the documents using NMT for translation. So now we have index for all of these systems. We also process the queries according to the relevant setup. For example, in the SMT post-lemma and pre-lemma, we lemmatized the query. And we used for lemmatization, we used the Morphidata and the Snowball for stemming. So here are the results from SMT and NMT using this different setup. We still, the interesting fact that, let's start from DT SMT form. This is the SMT, the document translation, and the yellow one is the query translation. We can see that the difference is significant actually in favor of query translation. So query translation is better than document translation. However, this conclusion can be applied. We are not sure, but we have to consider the domain, right? Because we are working in the medical domain, and as we might know in the queries contain symptoms, and maybe we don't need linguistic information to translate symptoms in queries or medical conditions. Also, we can see that the morphological processing didn't help us to improve the results. Maybe because lemmatizing or stemming medical terms is not easy as we might expect as like the general domain terms. We can also notice that NMT didn't perform well on document translation, and it's expected because NMT doesn't do well on long sentences, as also reported by Cohen and Knowles. Where's the DT? So this is the document translation using NMT, and we can see comparing to the DT SMT form. yeah, to the blue one. Well, it outperformed the SMT, but comparing to the, we were expecting better results for, like as we noticed in query translation, but it's still, I don't have pointer here, right? It still couldn't outperform query translation. And, sorry. So that was everything, and I hope that you have some questions or comments on my work. Basically, like I presented everything that I have done during my PhD. These last findings we submitted to ACL, and we are waiting for the results. The first round of the reviews was really harsh. Not harsh. I mean, we got nice comments or score at the end, but we had a lot of questions, so we hope that we answered them. And yep, that's all. So, any questions?
Thank you. Thank you very much for your talk, and especially for the conclusions which you suggested in the end. So now questions or queries or whatever.
Do you have any question about the subtitling?
Yes.
Not about the subtitles, but you talked about at one point about some basically query expansion algorithms, and you basically train some models to do that.
Yes.
You tried using basically just a paraphrasing model or paraphrasing toolkits to do the same task. I don't know if that would be helpful.
Like,
combining it with your model would be helpful, but it's just an idea that occurs to me right now.
Yeah, actually, I haven't tried it, and like I remember I thought about it, and then I said, okay, so we don't care about word order. We just want to keep the original query and add relevant terms to it, because we consider the query as and the documents as a bag of words. So.
Makes sense.
Mm-hmm.
Yeah, Martin.
I have a question about the search engine. You said that it doesn't care about the position, it takes it just as a bank of words query. So have you tried treating it as bigrams, for example, or detecting some phrases? And
Yeah, actually, that was the like the beginning of my research. At the beginning of my research, I wanted to design a good monolingual system where I have English queries and document queries before getting into cross-lingual IR. And I used some language model to consider like bigram or trigram, but actually it didn't work comparing to unigram. So I fixed this system. I said, okay, so this is the best system I can reach in monolingual data, and let's move to cross-lingual data and reduce it to monolingual task by doing translation. So I didn't investigate that again. Actually, maybe things changed, or maybe I should look at it.
Maybe one more thing. You were basically when you did that was actually pretty interesting when you did the data filtering for NMT, because I actually found a similar thing in natural language generation, where it turns out that neural models are really sensitive to
Yes.
the data.
Yeah.
But you said that you basically filtered the data to get the correct language all the time, right? Or was it? I mean,
well, we had to, like, we observed two things in the data. First thing, there was let's say missing translation.
okay.
So both lines were in English, and in the German part we noticed swap. So these are parallel data, but actually the English one should be in the German's. So what we did, like if I put some threshold for the length difference, like it was something like 5 or something like, I just wanted to avoid empty or short sentences and long one. So if they are like somehow similar in length, swap them. And if each one contains a stop word from the relevant language.
That's actually what I wondered, if it would be helpful to use like a language ID tool instead of list of stop words.
I'm pretty sure
that would be like an overkill, or
I'm pretty sure it will be more effective. Yeah, but yeah,
just like those simple stupid.
yeah, I did it. It was simple, and we were able to outperform the monolingual.
Okay.
Even the one, so we said, okay, that's interesting, and the results are consistent in all of languages. So
Okay.
let's stop here. But I'm pretty sure it's worth investigating. Like we should think more about data cleaning. And actually, thanks to the paper from Martin and Andre, tips for NMT training. Like I was inspired by this from that papers.
We have a very naive suggestion. When you compare the query-based translation against the document-based translation, you said that the original suggestion or idea or results showed that the document translation was supposed to be better than the query translation. And I just wondered why this might have been so. And it occurred to me that maybe in the document translation you have more context on which you can, on which the translation, or from which the translation can be derived, or while in the query translation you have just a very small context. So it might be so that it's not that easy to translate, or is it just crazy?
Well, like you mean we are not using the linguistic information in the document in effective way, or we are not using the linguistic information documents correctly, right? Actually, like there might be some explanations for that. What we did, like these documents were in HTML format. So we cleaned the documents by stripping off HTML scripts. So and then we did the sentence segmentation to avoid long sentences. So maybe here in this case we were not lucky, or we lost a lot of context and linguistics information by splitting sentences or by cleaning the data, because we know that in HTML code we have a lot of noise, like scripts together and some menu in the left side, or footer, header. Maybe we lost the important information for decoding. I think that might be the reason for that.
Thank you. I don't see any hand up, so may I guess that there are no further questions or suggestions. So let me thank the speaker again for his talk, and we are looking forward to the progress, I would say. So thank you very much.
Thank you.